Well, hello and welcome. I have to say that it is a beautiful day outside. I have the window open and the sunshine streaming in, and I certainly hope it's a beautiful day where you are. And maybe if not, what can you do to make it better? But in any case, let's study some parabolas today. So get yourself some paper and pencil, because when you think you should be writing and when you are writing you should be thinking, those two things go best when they go together. And so let's talk today about the second conic section. That would be a parabola. The first conic section was a circle, which is what you get when you slice a cone parallel to the base. A parabola is what you get when you slice a cone parallel to one of the sides, so that the angle that you slice it at compared to the base is the same as the angle of the side. And so then let's actually switch over to the iPad. There we go. All right, so the parabola, again, if we're doing it with Euclidean geometry, it's the collection of all points equidistant from a line and a point not on the line. So let me kind of reach in here now and let's discuss some vocabulary and some principles for this. So I've got a point and I've got a line, and the point is not on that line, they're in blue, and then I have the parabola in red. The point has got a special name. This point is called the focus. And the line has a special name. It's called the directrix. So like the word direct and then make a trix out of it. Okay, the focus and the directrix. Now, again, let's just double check, because what we're saying is that for any point on the parabola, it is the same distance to the focus and it is the same distance to the directrix. So let me take this point right here in black. This is just some x and a y now, because we're going to do it on a Cartesian coordinate grid. But let's just see. What's the distance from the point on the parabola to the focus? I count 1, 2, 3, 4, 5, 6, 7, 8. 8 units. Then let's count the distance from the point on the parabola to the directrix. 1, 2, 3, 4, 5, 6, 7, 8. Also 8 units. There we go. So that point there, the xy, is on the parabola. And you can now do that for any point. The distance between this point and the focus must be the same as the distance between that point and the directrix. So anywhere along here, like say this point over here, there down to there has to be the same distance. Okay? So now let's actually start to talk about what this means in terms of a Cartesian sort of arrangement. But before I do that, let's talk about a special distance. So let me erase some of these things here. The distance from the point down at the very, very bottom, which you should know already is called the vertex. It's the lowest point, or that's the part where the curvature changes on a parabola. The distance from the vertex to the focus, we're going to call that f. It's also, if you think about it, it has to be the distance from the vertex to the directrix, also f. Right? Because the vertex has to be equally spaced between the point called the focus and the line called the directrix. But now I have a new line I want to talk about, and let's see if I can do that in green. I want to talk about the line that goes straight from the focus to the parabola on the left, and straight from the focus to the parabola on the right. Well, you can see that line there in green. This entire distance right here is called the latus rectum, which means straight to the side. It's got to be parallel to the directrix, and it's going to go through the focus straight to the sides. Interestingly enough, the latus rectum has a distance of 4 times f. Whatever f is, the distance from the vertex to the focus or from the vertex to the directrix, the latus rectum is quadruple that. So let's just double check. How far is it from the focus to the vertex? Looks like 4 units. How far is it from end to end? From this point right over here. I count 1, 2, 3, 4, 5, 6, 7, 8 to the focus, and then 1, 2, 3, 4, 5, 6, 7, 8. This is going to be 16. Voila! There we go. So this kind of arrangement then is true of all parabolas, no matter how they're oriented. And I say that I wanted to do the circle one before I did the parabola here, and I told you because the math is complicated. And let me explain what I mean by that. Let me kind of remove some clutter here. So if I take a point on the parabola, call it this point right here, I have the distance to the focus, and I have the distance to the directrix. What I have to do, since those are equal, is I have to set up a little equation here, and I have to say that the distance to the focus is equal to the distance to the directrix, and then I'm going to have a point. This is going to be my x, and this is going to be my y, and so I'm going to have a distance formula. Some kind of big long distance formula is equal to some distance over here, maybe another distance formula, so to speak. And that math can actually get pretty complicated. In addition to that, the two distances that have to be equal. In addition to that, I've also got a right triangle going on right here in blue. And so then I'm also going to have to do the Pythagorean theorem, where this is C and maybe this is an A and this is a B. I have to say that C squared is equal to A squared plus B squared. But you'll notice the distance here, the hypotenuse is the same as maybe the distance to the focus. Those two are equal to each other. So by some substitutions and some rearrangings and things like that, you can work it down to the Cartesian equation that we're going to get to. But it's really complicated, and like I don't want to lay that complicated math on you. The circle one was really quite easy. It was just the Pythagorean theorem, right? That was really kind of simple. This one involves some rather complicated math to get us to where we need to go, which is why I said it probably didn't need to come first. Okay, so for now, any kind of parabola, you're going to have that following arrangement. You're going to have a U shape somewhere. Your focus is going to be in the middle, and then your directrix is going to be on the other side of the vertex, no matter where it goes. Now you can have one that that opens sideways. We're going to do parabolas that look like this, and it will have a focus in the middle, and it will have a line, the directrix, on the other side. You could even go the opposite direction. You could have a parabola that opens to the left, and it would have a focus in the middle, and it would have a directrix on the other side. Or you could even have one, as you probably have already had, a parabola that opens down, and you're going to have a focus in the middle and the directrix kind of on the other side. If you really wanted to get complicated, you could make them like diagonal. Cartesian-wise, that's very complicated. But I have to tell you, I had a student one time years ago who, when I was explaining this, she piped up in class and she said, "Oh, the fruit goes in the bowl and the bowl goes on the table." And I said, "What?" She said, "The fruit goes in the bowl and the bowl goes on the table." I said, "I don't know what you're talking about." I was like, can you show me what's going on here?" She said, "Yeah." So she came up to the board, if I remember right, and she said, "Look, this is the focus, right?" She says, "It's like a piece of fruit. And the parabola is like a bowl. And it goes on top of the table." And I was like, so Shannon, if you're watching, I have always used this since that day, and there are lots of people who know your Shannon principle that you've never met, so you're famous on the internet. But I thought, that's nice. All right, so here we go. Here's our fruit in the bowl on the table. Let's see if I can get in here and make it easily seen. I'll do blue, I'll make it bold, okay? Obviously the parabola is going to be the bowl. There's the bowl. Here's your piece of fruit. It's labeled F for fruit or F for focus. And then it sits on the table. There we go. So your parabola always has the focus on the inside, and then the directrix is on the other side like that. Fruit sits in the bowl that sits on the table. I like it. Now, one of the interesting properties of a parabola is actually the fact that it does, like, literally focus things. You say, what are you talking about? Well, if you make like a mirror or some kind of reflector out of the parabola shape, the curve shape, if it's parabolic, not just spherical or a circle, but a parabola, here's one of the properties. If you put like a light source right here at the focus and light goes in all directions, it will go there and it'll go here and it'll go here and it'll go maybe down there and it'll go over there to that side and maybe over here to the side. If you put a light at the focal point, at the focus, when the light is reflected off of the internal surface here, it will come out parallel to itself. It will be what's called collimated. So all of this light then will go forwards. And so you can really use it to direct light. You're not wasting any light. It's like a focused beam that goes forwards. And the path is reversible. If you've got some kind of device that you need to collect certain things. Oh, that was a terrible parabola. Let me try again. Like this? Okay, that's good enough. And you've got incoming information like radio waves or something like that. It will be reflected all to a similar point. No matter where it hits, it'll be reflected to the focal point. So maybe you're used to seeing like a, I don't know, like a satellite dish or something like that, and it's got some kind of like arm that comes out with a little box that sits right there, and then you're like, oh, that's what's going on, is it's reflecting all the things to that location in space. And that's really kind of neat. All right, so now let's go down and let's do some algebraic modeling here. If you're familiar like with basic quadratics, here's what we've got. We've got one that opens up or down. It would look like this. Y is equal to a times x minus h squared plus k. Where h and k are your vertex, right? And this one would open up or down, so it would be a parabola that maybe would do something like this. And then there's your focus, and then your vertex right here is the point H and K. And now let's talk about some particular things. You know that if A is positive A, it opens up. And if it's negative A, it opens down. But there's something involving the number. Your focal distance, if you want to call it that, the distance between the vertex and your focus, that distance right in there, F. F is equal to 1 over 4A. You should memorize that. Okay? The distance from the vertex to the focus is 1 over 4A, and that's also the distance from the vertex to the directrix, that line underneath. That also would be 1 over 4A. 1 over 4A. All right? And then the line that goes straight through the focus that connects the sides, straight to the sides, the latus rectum, is going to be equal to 4F. Or it would be 1 over A, the absolute value, because it's not a negative. Okay? If you wanted to take that F, you can actually swap the F and the A. If I solve this for A, it would be A is equal to 1 over 4F. Right, the A comes to the numerator, the F goes down to the denominator. Alrighty, so that's one that opens up and down. However, we can also have one on Cartesian space that opens left and right. That would look like this. X is equal to A times Y minus K squared plus H. say, what? Yeah, that one would open left or right. So on a Cartesian grid, it might look like this. Okay, so now if A is positive, it opens right. And if A is negative, it opens left. Okay, and the same thing is true for the focus and the lattice rectum. Those principles are the same. Interesting thing here, you notice that the lattice rectum is 4 times the focal length, and then there's the focal length which is equal to 1 over 4a. Why is this property of parabolas involving 4s? Like, why doesn't it involve 3s or 5s? Why 4s? 4s in particular. 4s seem to have a home here with the parabola. Why is that? Why not 3? Why not 7? Why 4? I don't know. It's mysterious to me. If you could think of a reason why it's 4, why it must be 4. It is 4. We know that for certain. Why must it be 4? That's a different kind of a question. I'm open to suggestions. Okay, now let's see if we can put this to use and actually do some Cartesian math out of it. All right, so example number 1. Write the equation in standard form. Identify the vertex, axis of symmetry, and direction of opening of the parabola. All right, standard form is either going to be the 2 that I just gave you. Now, the first thing I'm noticing is that it's my x that's squared, not the y. So this one opens up or down. This is the ones like you've done in previously, perhaps with quadratics. Okay, so standard form would be y is equal to a times x minus h squared plus k. So this is probably not a new problem for you. It's probably very similar to one that you've done before. But I have to get it in standard form. So I see, let me rewrite this first. Let me say y is equal to negative 2x squared plus 8x plus 10. Let me get it in descending degree. That's general form, by the way, that one right there. And now let me complete the square. In order to complete the square, I have to factor out the negative 2 from the x group. So it's negative 2 times x squared minus 4x, if you can track that math, you should be able to. Leave space, close the parenthesis now, and then plus 10. Now I have to complete the square inside with the blue. What's half of 4 and square it? Oh, add 4 in. But if I'm going to add 4 in to that group there, what do I do on the same side of the equation? I'm going to add in 8. Yes. You're confused maybe. Why would you add in 8? Why wouldn't you subtract 4? Because I really didn't add in 4 to the entire equation. I just added 4 inside the group. But you'll notice that sitting outside the group is the multiplier of negative 2. So when I put a plus 4 right here, what I'm really doing is I'm adding into the entire right-hand side negative 2 times 4, which was negative 8. So to counterbalance that, I need a positive 8 right there. Now I've really added in 0. So I haven't changed the value of the right side of the equation, although I am changing the form. Okay, so now I get y is equal to negative 2. This factors down into x minus 2 squared plus 18. Now I've got it into pieces where I can get what I want. Their standard form, I've answered that one. Identify the vertex. The vertex is hk, so that's going to be 2, 18. And axis of symmetry. So just if I do a real quick sketch, this is going to be a graph that opens up. It's going to be 2, 18, so it's going to hit here, and the a value is negative, so it's going to open down. It's going to look something like that. So my axis of symmetry is always going to be the vertical line for one that opens up and down, the vertical line that goes through the vertex. So the axis of symmetry is x equals 2, and it's going to open down because my a value there is negative. Okay, so there's my answers there. A sketch will always sort of help you see these things. You don't have to necessarily do it all analytically. these things are geometric. They involve space as well as just abstract numbers. And so seeing a picture is oftentimes very helpful. Just draw a simple sketch to help you kind of place the pieces in your mind. Your mind has to see the space. Okay? Now, example number 2. Graph the equation. Oh, these are normal. You've done ones like these before. Let me show you a little alternate way we can do it now. So the first thing we're going to do when we graph is we're going to start with the vertex. So the vertex is going to be equal to 3, 1. I'll plot that. 1, 2, 3, up 1. Okay, there's my vertex. Does it open up or down? Well, it opens up because the a value is positive. 1/8 is positive. So it opens up. Now I need to plot some more points. An easy point to pick would be to say let x is equal to 0 and find out what y is. If I plug x is equal to 0 in there, I get 1/8 times 0 minus 3 squared plus 1. Okay, so negative 3 squared, that's 9. I'm going to get 9 divided by 8 plus 1. That's maybe like 1 1/8. That's terrible. I never should do mixed numbers. You shouldn't either. I almost scribbled that out. 1 1/8 plus 1, 2 1/8. So y is equal to about 2 1/8, 2.125 if you know your eighths. So 2.125 right there. I know that there's an axis of symmetry vertically that comes through here. So if I know that point there on the left, 3 spaces, I'm going to go over 3 and come up 2 1/8 right here. Okay. But now there's another one that you can find real easy. Let's find the focus. Where's the focus? So the focus is going to be up above the vertex. But how far? The focal distance is going to be 1 over 4a. So the focal distance is equal to 1 over 4 times 1/8. Now don't let the compound fraction scare you. You should be able to manage these by now. That's equal to 1 over 4/8, which is 1/2. That's 2. So look here. The focus is up 2 points right there. I'm not going to plot a dot. I'm just going to plot an X right there to show me the space. Okay. So that's where the focus sits, and if you can see it, maybe it sits inside the bowl, right? The Shannon principle. But how long is the latus rectum? Well, the latus rectum is what? What did we say it was earlier? Latus rectum is equal to 4 times f. So 4 times 2 is going to be 8. Now that's the entire distance between the parabola on the right and the parabola on the left that goes through the focus. So I'm going to split the focus in the middle, and I'm going to go to the right. 1, 2, 3, 4. That point there has to be on the parabola, right? It's got to be 4 units. That was a terrible bracket. Let me try a better one over here. Nope. I went to the other point. The mathematics is not what I want it to be, but about certainty. 1, 2, 3, 4. That point right there. Here we go. That's also 4 units. And so the entire latus rectum there is going to be 8 going through the focus. So there we go. The vertex, the endpoints of the latus rectum, and maybe some intercepts then is another way that you can find some points and then draw yourself your smooth curve. Make it smooth, make it pretty. What's beautiful on geometry is also what's true. I find that interesting. If you have a beautiful parabola, it's probably a true parabola. Okay, and we didn't need to, but there's the directrix is down there, right? 2 units down below, but we didn't need to graph that. We weren't asked to graph that. Okay, it just says graph the equation. All right? So now let's try this one. Write the equation in standard form, then graph the equation. The vertex at 4, -1, and the directrix at x is equal to 3. Okay, so the vertex 4, -1. Let me plot that point. That's 1, 2, 3, 4, -1 right there. And then the directrix is x is equal to -3. Is the directrix a point or a line? It's a line. What kind of line is x is equal to 3? It means all x's are 3. So that means here's an x of 3, and here's an x of 3, and there's an x of 3. Here's the directrix. Let me make it a little thicker here so that you really can see it. There's the directrix. Which way does this parabola open? It opens to the right. Can you see that? That's the table. The vertex is the bowl. How does the bowl sit if it sits on the table? The bowl is going to sit something like that in here, and then the focus is going to sit like that in there. So this is one that actually opens to the right. This is one of these y squared ones, not x squared. Now I just did a little sketch right there with the parabola. I'm not sure that that's actually it. I need some more points. But in any case, this is one that opens sideways. So we have to do now write the equation in standard form. What is that going to be? It's going to be x is equal to a times y minus k squared plus h. Well, I know h and k. That's going to be 4 and negative 1. What I have to do now is I have to find a. How do I find out what a is? Well, if you know the distance right in here, this is going to be f. And the distance to the focus is also going to be f. Here's my focus right there in blue. So my f is going to be equal to 1 unit. That'll help me figure out then what the a value is, because a, as we said, was 1 over 4f. So that's equal to 1 over 4 times 1. My a value was 1. So if I put these pieces together now, x is equal to 1 times y minus, what's the k value? A negative 1 squared, and then plus h, so plus 4. There's my equation, although I have to admit the one there is a newbie thing. I maybe wouldn't write that, but it's not technically wrong, but you noob. Okay, there we go. And now we're supposed to graph the equation. Okay, graph it. Well, there's the vertex. And I can let y is equal to 0. So let's let y is equal to 0. That will give me an intercept. So if I do y is equal to 0, that gives me x is equal to 0 plus 1 squared plus 4. Isn't x is equal to 5 there on that one? So if I come over here, let me erase some of the clutter here. Get rid of that one too. So x is 1, 2, 3, 4, 5. Here's a point. Right there. And there's another point right there. Wait a sec, somehow I'm not feeling that. Oh, I know, I see what I did. Found it again. When you make a mistake, when you feel this conflict in your mind, oh, something's not working out right, be patient, be thoughtful. You probably saw it before I did. I got so excited about that when I was thinking about the next thing. It's 1/4, which really means I do need a 1/4 right here. There we go. I thought that was a little too tight. You get a feel for these after you do enough of those. I was like, that curvature is really kind of too fast for that focal point. So yeah, those are wrong. X is not 5. X is going to be equal to 1/4 plus 4, so 4.25. So maybe like right there and then right there. Good. And I got an axis of symmetry that now comes through here. That's y is equal to negative 1. That's not part of the graph though. I'm just pointing out that it's symmetric. Okay. And then now let's do our lattice rectum if you like. Lattice rectum straight to the side. That's equal to 4 times f. Well, that was going to be equal to 4 times, what was f? I think we said it was 1, right? Yeah, the distance between the vertex and the directrix. 4 times 1, so the lattice rectum is 4. Which means from the focal point, which is right here, I need to split it and go 2 up. 1, 2, that point right there, and then come down 1, 2, that point right there, and now I've got my parabola, smooth curve, got my parabola that opens to the right. Okay? Now, if you've got a textbook and you're looking at your textbook, there's two different schools of thought. I've taught you now from the school of thought that says understand the principles and how the pieces fit together and then think your way through it. Another school of thought says memorize all of this information and then just follow the formulas if you want to. you probably have a chart in your book that looks something like this. This is a parabola standard form. The x is squared, so this is a parabola that opens up or down. This one over here has got x, and it's the y value that's squared, and so this is going to be a parabola that opens left or right. And then you got your axis of symmetry and your vertex, and then look at this. They're finding the focus by doing like, it's the h value, then it's k plus 1 over 4a. What is 1 over 4a? That's your f. But I don't want you to necessarily memorize a formula. Oh, the vertex is hk, and so that means, what were we even talking about here? Oh, the focus. The focus is h, comma, and then k plus 1. You'll never remember that. If you can, fantastic. I can't. I'd have to go look it up. The only thing that I really need to remember is the Shannon principle, and that is that when I have a parabola, it's got a focus in here in the middle, and then it's got a directrix, and the fruit sits in the bowl that goes on the table, and this distance in here, right there, that's f, and f is equal to 1 over 4a. That's what I've got in my head. And so now, whichever way the problem calls for it, if it's got a vertical line and a focus to the left, then I know that it's going to have to open that way. Or if it's got a horizontal line as a directrix and then it opens down, I know that the focus is lower than that. I think my way through the spatial positioning of these things rather than memorize a formula like this. But I'll leave it to you if you want to memorize all of that and can commit it to memory and then use it as a tool of reasoning. Good luck. Okay. But in the end, it's much better to be able to think and use math then as a tool of reasoning, of thinking your way through a process, even if you're slower, than to simply memorize things and not know what you're doing. One school of thought says memorize and mimic. The other school of thought says think and understand. And sometimes the people in the first group are faster, in a sense, than the people in the second group. But the people in the second group, even if they may be slower, they can adapt to change. They can think through a problem that's different than the one they've been shown. If you show the first group a problem that they've never seen before, they think, I can't do this. You've never shown me how to do it. I can't imitate you if you haven't shown me how to do it first. The second group can probably take the principles and apply them and think through the process. And this second group, the people who are able to think and reason and understand, that's preferred. Please don't be satisfied just with memorization and mimicry. Notice I say didn't. There are some things you need to memorize. But don't be satisfied just with memorization and mimicry. Think and understand. Back to me. It's still a beautiful day outside. You should get out. I mean, even if it's not all that nice, find a time to get out of your house and enjoy the outdoors. The outdoors are good. There's mathematics in the outdoors, right? Galileo said parabolas were first seen in projectile motions. Go outside and throw a rock up in the air, or I don't know, a dirt clod or something like that. And just make some parabolas outside. Anyway, may your days be merry and bright, and may all your mathematics be right.